Vertical alignment is viewed from the side, which is known as the profile view. And when we're looking at vertical alignment, we see the elevation on the y-axis and then the horizontal distance on the x-axis. Two basic types of curves. The first is the Crest vertical curve, and this is the concave down shape, and then we have a concave up shape, which is the sag vertical curve. So those are the two general types. We also have some additional subsections of those types of curves as well. So on the left here, we've got three types of crest curves, and on the right, we've got three types of sag curves. We're going to talk through each of these. So in our first crest curve here, we have, which is similar to the example I showed on the previous slide, where we have a positive grade and then a negative grade, and that creates kind of a nice crest curve. We can also have the situation where we have the first grade is kind of steeper, and then the second grade is flatter, and that causes that crest shape. And then the third possibility is your first grade is a downgrade that's fairly flat, and then the second one is a steeper downgrade, and that also creates that crest shape. Similarly, for sag curves, the example that I showed previously is a downgrade followed by an upgrade, and that creates that nice sag shape. We also can have a steeper negative downgrade followed by a flatter downgrade, and we see that's going to result in a sag. And finally, a flatter upgrade followed by a steeper upgrade is also going to give us a sag vertical curve. So one of the important things to know for vertical alignment is the length is not measured along the curve. It doesn't take into consideration the curvature. It's measured horizontally. The y-axis is the elevation of the alignment. And again, distances are measured as horizontal distances. And the reason why we have to do that is we only want one set of stationing. That stationing goes along our horizontal alignment. If we measured along vertical curves, it's going to give us a whole separate set of measurements. So that's why for highway alignment, everything is done in horizontal distances. So that length is going to be that horizontal distance only, not accounting for vertical curvature, only the horizontal side. So some of the key points of interest for our vertical curves. We've got our entrance grade G1 and our exit grade G2. So those are the straight portions of our vertical alignment, and this is where we transition from those grades to our simple parabolic curve. The length is the straight line distance from the PVC to the PVT. The place where the grades intersect is the PVI, the point of vertical intersection. The place where the curve begins is the point of vertical curvature, the PVC. And the PVT is the place where the curve ends and you return to the grade. That's the point of vertical tangency, PVT. We also can calculate the algebraic difference in grades, which is A. So this is equal to the absolute value of G2 minus G1. And for a symmetric parabolic curve, half of the length of the curve is on each side of the PVI. So our L over 2 is from the PVI to the PVC, and it's also equal to this distance from the PVI to the PVT. The parabolic equation defines our symmetric parabolic curves when we're using vertical alignment. Y equals C plus BX plus AX squared, where the term C is the elevation of the PVC, which is Y PVC. B is just our entrance grade, G1. And the important thing for grades in vertical curves is that the grades need to be in percent, and you need to apply a negative for downgrades and a positive for upgrades. And A is G2 minus G1 divided by 2 times the length. In this case, for our parabolic equation, lengths are in stations. So X is the distance from the PVC to the point of interest on the curve, and that needs to be in stations. So if it's 400 feet, that is 4 stations. The length of the vertical curve is L, And this is measured horizontally, as we've talked about, and it's also in stations. And our y is our elevation on the curve at a distance x from the PVC in feet. So our curve elevation equation, so the elevation on the curve is y PVC, the elevation of the PVC, plus g1 times x, plus x squared times g2 minus g1 over 2 times the length. And the two most common sources of error that I've seen when applying the parabolic equation to vertical curves, first is your grades. The error is putting them in decimal form instead of percent, so make sure you input 3% as 3 and not as 0.03. And the length x should be in stations, not feet. So the common error is putting it in feet. So instead of inputting a length of 1,000 feet as the number 1,000, you should input it as 10 stations. So we can find the high or low point of a vertical curve. And if we recall back to calculus, the derivative of the parabolic equation provides the slope. So setting the slope equal to 0 allows for solving for the high or low point. So there's our parabolic equation. You can take the derivative of that equation, setting it equal to 0, and solve for what will be x sub m, and that's the distance from the PVC. It's not the stationing, it's just the distance from the PVC. And we can add x to the PVC station to get the station of the high or low point. So the equation is x sub m equals g1 times L divided by g1 minus g2. So reviewing some additional equations here, we're looking at a vertical curve. We can see that the tangent offset at the PVI can be calculated with E, where E is equal to A times L divided by 2 squared, where A, again, if we recall from the previous slides, G2 minus G1 divided by 2 times the length. And we can also see here X and Y. So X is our horizontal distance from the PVC to a particular point of interest on the curve. Y is the tangent offset. And so the equation for at any point, the elevation on the tangent for a particular vertical curve is the elevation of the PVC, y PVC, plus G1 times X equals also the elevation of the PVI, y PVI, plus G2 times X minus L divided by 2. And so there's these two equations here, and they apply to different portions of our vertical curve. So on the side of the PVC from the PVI, the equation of the tangent elevation is the elevation of the PVC plus G1 times X. This is just the grade times that length, or that distance X. So not a very complicated equation. And then for the portion from the PVI to the PVT, you start with a PVI elevation and then add G2 times X minus L over 2. So it's important that we make the distinction. There's two components here in this equation for the elevation on the tangent for this vertical curve. If you're on the left side of the PVI, you need to use the y PVC plus G1 times X. And if you're on the right side of the PVI, you need to use the equation y PVI plus G2 times X minus L over 2. For stationing purposes, the station of the PVC is the PVI minus L divided by 2. So the PVT is equal to the PVC plus the length of the curve. And the PVT also is equal to the PVI station plus the length divided by 2. And again, all these lengths are horizontal distances, so we don't have to account for the effect of grade in these distances. So it really simplifies things for vertical curve stationing compared to horizontal curves. And this, what you will need, will change depending on what information is given in the problem. If you're given the station of the PVC, obviously use that equation for the PVT to find PVC plus L gives us the PVT station if that's what you're asked for. So you really have to look and use combinations of these equations that are appropriate for the givens that you have for the problem. Some more equations here. The PVC elevation is equal to the elevation of the PVI minus G1 times L over 2. Okay, so just one more tip on our equations before we move into some example problems. The PVT elevation, also the Y sub PVT in those terms, can be used as a check of the parabolic equation. Because we can solve it geometrically, if we recall these equations, you can find the elevation of the PVT with our equation on the right. So we can use this equation for a given PVI elevation, G2 times X, and in this case, the X will be equal to L minus L over 2 to find this point Y PVT. And that can be used again as a check of the parabolic equation because we can solve this geometrically. So input L both into this equation to find the Y PVT geometrically. And then we can check our parabolic equation by plugging in L for X. So example 1, we're told that we have a curve with a PVI at station 34 plus 93 that has an elevation of 346.29 feet and a PVC station at 30 plus 13. We're told that the entrance grade is 4.2% and the exit grade is negative 2.8%. We're told to find the equation that defines the curve. So to solve this problem, we don't actually need to have a full solution because the goal is just to answer the question, meaning that eliminating 3 incorrect answers will make you just as successful as a full solution. So first, notice the 3 components in each possible answer, A, B, and C, in terms of our parabolic equation components. There's no difference in terms of the C, which is the elevation of the PVC. So solving that part will not help us in the problem. So we don't need to worry about C. There's no difference there. We can focus on just A and B. So next we should start with the easier of the remaining components, which is B, which is equal to G1. So G1, the entrance grade, is given in the problem statement as 4.2%. Therefore, answers B and C can be eliminated. So this just leaves us with A and D. But this will require solving for part A of the parabolic equation. So A equals G2 minus G1 divided by 2 times the length. The length is our distance between our PVC and PVI, multiplied by 2 gives us 9.6 stations. So A equals negative 2.8 minus 4.2 divided by 2 times 9.6 stations gives us an A of negative 0.36458. And that means the answer is A. We're told we have a curve with a PVI at station 34 plus 93 and a PVC at station 30 plus 13. What is the length of this curve? A simple drawing regularly can be helpful. So we've got our PVI 34 plus 93. We've got our PVC of 30 plus 13. We know that this is half the length. So with a symmetric parabolic curve, this is also equal to L over 2. So some simple math is going to help us solve this problem. Remember, distances are horizontal, vertical curves are assumed to be symmetric parabolic curves. Use the relationship between the length and the locations of PVI, PVC, and PVT to solve this problem. So the PVC equals the PVI minus L over 2. So plugging in our values, 30 plus 13 equals 34 plus 93 minus L over 2. Rearrange that so L equals 34 plus 93 minus 30 plus 13 multiplied by 2. Gives us a length of 960 feet. And that is answer D. And again, if we were using L in any of the problems or any of our equations, we need to input that as 9.6 stations, which is the same as 960 feet. We're given very similar information here. PVI station, PVC, elevation at the PVI of 346.29, entrance grade 4.2, exit grade negative 2.8. We're asked to find the elevation of the PVC. Again, a drawing can be very helpful, so plugging in the information we know here in a simple graphic can really be helpful. And the approach for this problem is to account for the slope and the length of the tangent to find the elevation of the PVC. So that PVC elevation, again, is the PVI elevation minus G1 times L over 2. So rearranging this, L over 2 is the PVI elevation minus the PVC elevation. So solving for the PVC elevation, this is equal to 346.29 feet. That's the elevation at our PVI, minus 4.2% times 34 plus 93 minus 30 plus 13. That's equal to L over 2, just based on our stationing, because this is the distance from the PVI to the PVC, and we know that that equals L over 2. So that's why we're plugging in those difference in stations is the same as this L over 2 here. So our PVC elevation, 346.29 minus 0.042 times 480 feet. You could also do that in percent and stations, so you can multiply just the number 4.2 times 4.8 stations will also give us a PVC elevation of 326.13 feet. And that is answer B. Given the same curve information here, now we're asked to find the elevation of the PVT. Again, a nice simple drawing can be useful. In this problem, we want to account for the slope and length of the tangent to find the elevation of the PVT. So the PVT elevation is the PVI elevation plus G2 times L over 2. We're going all the way to that PVT. So L over 2 equals the PVI minus PVC. So the PVT elevation is 346.29 feet. That's the PVI elevation plus G2 times half that length, which is negative 2.8% times 34 plus 93 minus 30 plus 13. So our PVT elevation is 346.29 feet plus negative 0.028 times 480 feet. Again, that could be negative 2.8 times 4.8 stations, to be consistent with your units there. Gives us a PVT elevation of 332.85 feet. And that is answer C. We're given our same curve here. Now we're told that it's defined by this parabolic equation. The elevation on the curve y is equal to 326.13 plus 4.2x minus 0.36458x squared. And we're asked for the elevation at station 38. So here's our very simple curve layout with some of the given inputs. And we need to determine if the point of interest is on the curve, and then determine its distance from the PVC, which is x. So the curve starts at the PVC, station 30 plus 13, and goes to the PVT, which is the PVC plus the length. So the PVT equals the PVC plus the length. The length is the distance from the PVC to the PVI times 2. That's just our given information. So the PVT is at station 39 plus 73. So therefore, the point of interest, station 38, is on the curve. It's between station 30 plus 13 and 39 plus 73. So this problem can be solved with our parabolic equation. If it wasn't on the curve, we could solve it even more simply by just looking at the grade and the distance given any elevation that is provided. So next we need to find the distance to our point of interest, x. So that's just station 38 minus 30 plus 13 gives us a distance, x, of 7 plus 87. So that's 7.87 stations, or 787 feet. So next, the x 7.87 stations can be input into the parabolic equation. Y equals 326 plus 13 plus 4.2x minus 0.36458x squared. So plugging in 7.87 in the equation, we're going to get a y, or an elevation, at x of 7.87 of 336.6 feet. And that is answer B. Next, we're given very similar information. This time we're told to find the station of the high point. So again, a nice drawing. We also know for this we're going to use the equation for the location of the high point, x sub m, which is equal to negative g1 times L over g2 minus g1. So we're going to use that equation to find the location of the high point, which again is just a derivative of the parabolic equation, setting the slope equal to 0 to find that equation or use that equation. So x sub m, again, negative g1 times L over g2 minus g1. The length is the distance from the PVI to the PVC, that was the given, times 2 because we have a symmetric parabolic curve, so the length is 9.6 stations. Plugging that into our equation for x sub m, negative 4.2 times 9.6 stations divided by negative 2.8 minus 4.2 gives us a distance of 5.76 stations from the PVC to reach the high point of this curve. Now we can find the station by adding x sub m to the station of the PVC. Our station of our PVC was 30 plus 13. We had 5.76 stations to get the station of the high point of 35 plus 89. And that is answer B. Same information, now we're asked to find the elevation of the high point. Again, nice simple drawing. We've already solved for the location of the high point. And that is 5.76 stations. So we would have needed to solve that the same way we looked in the previous example. So building on that value though, for this one, we know our x sub m is 5.76 stations. We want to plug that value of x into our parabolic equation. So plugging in 5.76 gives us an elevation of the high point of 338.23 feet. And that is answer B. Now there's a little bit of information on vertical curve design. Vertical curve design is based on sight distance consideration, so it is important that we know what type of curve and what type of sight distance controls in a given scenario. And the computations that we use for vertical curve design are based on the algebraic difference in grades, which is known as A. And then the rate of vertical curvature, K, which defines the curvature. So that's the distance you need to travel per 1% change in grade. Stopping sight distance applies to both crest curves and sag vertical curves. And passing sight distance is only applied to crest curves. So the basic equation to determine the minimum length is shown below. The equation is the same for various curve types and types of sight distance. The K is what changes for each scenario. And additionally, the minimum length is 3 times the design speed. So any value you come up with length, we need to check it and make sure it's at least 3 times the design speed. So K equals L divided by A, or L equals K times A. So for any vertical curve, these are the equations we're going to use. L is going to give us that length of curve, the minimum length of curve in feet. K is the rate of vertical curvature, and that's what's going to change depending on which type of curve and which sight distance you have. And A is the algebraic difference in grades. So a driver's ability to see upcoming obstructions can be blocked by the highway itself. So when we're thinking about a crest vertical curve, we're thinking about a vehicle coming up one of the grades, and can they see some object over here? And the standard assumption for the Green Book is that the driver's eye height, so if here's the vehicle over here, that the height of the driver's eyes is 3.5 feet above the pavement, and that the object height is 2 feet. And the common assumption there is, so you can see the tail light of a typical car as you cross the Crest curve or some obstruction that's approximately 2 feet in the roadway. Passing sight distance, and this is only for 2-lane, 2-way roadways, assumes that an object height of 3.5 feet. So for passing sight distance, we're going to use 3.5 feet instead of 2 feet for our object. And what we're looking at there is for basically the roof of an opposing vehicle, because if you're passing on a crest vertical curve, you're going to be in the opposite lane, and so you need to be able to see a vehicle that's coming in your same direction. So for sag vertical curves, though, nighttime conditions are the constraining factors for sight distance. So what can happen is the headlights of the vehicle really are the thing that limit the driver's ability to perceive obstructions. And the computations for an appropriate sag curve length include the assumption of a 1-degree angle above the headlight direction. And so what we're looking at for our sag vertical curves is, here would be kind of the straight portion of the headlights. We're going to assume a 1 degree deviation there to see what's on the other side of the curve. So what we're worried about for a sag vertical curve is something is in the roadway that the headlights of the vehicle don't illuminate. And so as the vehicle moves through the curve, the vehicle's headlights illuminate what's on the curve, and hopefully a driver can see and react to any potential obstruction there. Obviously, street lighting, roadside lighting can help with these types of situations, but here's our standard assumption for sag curves, where the headlights of the vehicle are actually providing that ability to see something on the other side of the sag vertical curve. So the rate of vertical curvature K, this is in the Green Book, the most recent version. The 2018 edition is in tables 334, 35, and 36. And so the important things to see here are for sag curves, we're focused on stopping sight distance. So if you got a sag curve, here are your K values you'd use. And this again represents the feet you need to go to accommodate a 1% change in grade. That's why we're multiplying by A. That's our algebraic difference in grades. So for instance, this value 136, for every 1% change in grade, you need 136 feet in length to accommodate that transition. Next, for our crest curves, we either have stopping sight distance or passing sight distance. So we have K's that vary tremendously, so it is very important for any of these, we've got to know which type of curve we have. So for instance, there's 3 different K values here for 50 mile/hour design speed, 96 for sag stopping sight distance, 84 for stopping sight distance on a crest, and 229 for passing sight distance on a crest curve. And again, passing sight distance only applies to 2-lane, 2-direction roadways where passing is allowed, so that where you're going to allow that type of, the vehicle leaves their travel lane into the opposing lane of travel in order to pass a slower moving vehicle. So we've got to know what type of sight distance, what type of curve, and our design speed. And typically, if we aren't familiar with this, the design speed is typically 5 miles over the posted speed limit. So if you don't know exactly what the design speed is, but you know the posted speed limit, that usually will give you some sense of what the design speed should be. But it is common to have the design speed given in a problem. So let's look at a calculation for this. We're asked to determine the minimum length of a vertical curve to connect a 4.4% grade and a negative 3% grade on a 60 mile/hour multi-lane highway. So first we need to determine the rate of vertical curvature. That's the K value. When we have a positive entrance grade and a negative exit grade, that's a crest vertical curve. It's on a multi-lane highway, so stopping sight distance will apply. From the table, the appropriate rate of vertical curvature is 151. That's assuming the 60 mile per hour design speed. It wasn't explicitly given as a design speed, but that's what it's intended to be, that the speed is the design of the highway. And the algebraic difference in grades A can be computed as G2 minus G1, so 4.4% minus negative 3% gives us an A of 7.4%. And therefore, we can compute the length. L equals K times A, so 151 times 7.4 gives us a length of 1,117.4 feet. Again, that's the minimum, so the designer can choose to use a larger value if needed. And this value is acceptable because it exceeds the minimum vertical curve length of 180 feet. That's 3 times the design speed. So 60 mile per hour design speed in this case. So our minimum length is 180. So our 1,117.4 feet is an acceptable minimum length.